Welcome aboard, fellow enthusiasts, as we embark on another incredible video. Thank you for choosing our video on Base. Sit back, relax, and enjoy the ride. In computer programming, Base, also known as tetrasexagesimal, is a group of binary-to-text encoding schemes that transforms binary data into a sequence of printable characters limited to a set of 64 unique characters. More specifically, the source binary data is taken 6 bits at a time, then this group of 6 bits is mapped to one of 64 unique characters. As with all binary-to-text encoding schemes, Base is designed to carry data stored in binary formats across channels that only reliably support text content. Base is particularly prevalent on the World Wide Web, where one of its uses is the ability to embed image files or other binary assets inside textual assets such as HTML and CSS files. Base is also widely used for sending email attachments, because SMTP in its original form was designed to transport 7-bit ASCII characters only. Encoding an attachment as Base before sending, and then decoding when received, assures older SMTP servers will not interfere with the attachment. Base encoding causes an overhead of % relative to the size of the original binary data, 33% by the encoding itself, up to 4% more by the inserted line breaks. Brace yourself for a deep dive into design as we explore its impact and relevance in our evolving narrative. The particular set of 64 characters chosen to represent the 64-digit values for the base varies between implementations. The general strategy is to choose 64 characters that are common to most encodings and that are also printable. This combination leaves the data unlikely to be modified in transit through information systems, such as email, that were traditionally not 8-bit clean. For example, MIME's Base implementation uses OS, and for the first 62 values. Other variations share this property but differ in the symbols chosen for the last 2 values. An example is UTF-7. The earliest instances of this type of encoding were created for dial-up communication between systems running the same OS, for example. Encode for UNIX and BinHex for the TRS-80, later adapted for the Macintosh, and could therefore make more assumptions about what characters were safe to use. For instance, uEncode uses uppercase letters, digits, and many punctuation characters, but no lowercase. Let's now turn our gaze towards Base table from RFC 4648 and explore the fascinating connections it has to offer. This is the Base alphabet defined in RFC 4648. See also Base alphabet defined in RFC 4648. Brace yourselves for the next chapter, where we'll be dissecting examples. The example below uses ASCII text for simplicity, but this is not a typical use case, as it can already be safely transferred across all systems that can handle Base. The more typical use is to encode binary data such as an image. The resulting Base data will only contain 64 different ASCII characters, all of which can reliably be transferred across systems that may corrupt the raw source bytes. Here is a well-known idiom from distributed computing. When the quote without trailing white space is encoded into Base, it is represented as a byte sequence of 8-bit padded ASCII characters encoded in MIME's Base scheme as follows. Null lines and white spaces may be present anywhere but are to be ignored on decoding. In the above quote, the encoded value of man is foo. Encoded in ASCII, the characters M, and N are stored as the byte values 77, 97, and 110, which are the 8-bit binary values 1,000,000, 1,000, 101, 1,000,000, 100,001, and 1,000,000, 101,000, 110. These 3 values are joined together into a 24-bit string, producing 10 sextillion, 11 quintillion, 10 quadrillion, 110 trillion, 101,000,000, 101,110. Groups of 6 bits. 6 bits have a maximum of 6 different binary values are converted into individual numbers from start to end. In this case, there are 4 numbers in a 24-bit string, which are then converted into their corresponding base character values. As this example illustrates, base encoding converts 3 octets into 4 encoded characters. Encoding of the source string man in base. Padding characters might be added to make the last encoded block contain 4 base characters. Hexadecimal to octal transformation is useful to convert between binary and base. Such conversion is available for both advanced calculators and programming languages. For example, the hexadecimal representation of the 24 bits above is die. The octal representation is 23,260,556. Those 8 octal digits can be split into pairs, and each pair is converted to decimal to yield. Using those 4 decimal numbers as indices for the base alphabet, the corresponding ASCII characters are tfoo. If there are only 2 significant input octets, e.g., ma, or when the last input group contains only 2 octets, all 16 bits will be captured in the first 3 base digits, 18 bits. The 2 least significant bits of the last content-bearing 6-bit block will turn out to be 0, and discarded on decoding along with the succeeding equal padding character. If there is only 1 significant input octet, e.g., M, or when the last input group contains only 1 octet, all 8 bits will be captured in the first 2 base digits, 12 bits. The 4 least significant bits of the last content-bearing 6-bit block will turn out to be 0, and discarded on decoding along with the succeeding 2 equal padding characters. As we progress through this video, let's shift our attention towards output padding and uncover its hidden depths. Because base is a 6-bit encoding, and because the decoded values are divided into 8-bit octets, every 4 characters of base encoded text for sextets equal 24 bits represents 3 octets of unencoded text or data. 3 octets equal 24 bits. This means that when the length of the unencoded input is not a multiple of 3, the encoded output must have padding added so that its length is a multiple of 4. The padding character is, which indicates that no further bits are needed to fully encode the input. This is different from a, which means that the remaining bits are all zeros. The example below illustrates how truncating the input of the above quote changes the output padding. The padding character is not essential for decoding, since the number of missing bytes can be inferred from the length of the encoded text. In some implementations, the padding character is mandatory, while for others it is not used. An exception in which padding characters are required is when multiple base encoded files have been concatenated. Prepare yourself for an in-depth analysis of decoding base with padding in this section. When decoding base text, 4 characters are typically converted back to 3 bytes. The only exceptions are when padding characters exist. A single equal indicates that the 4 characters will decode to only 2 bytes, while indicates that the 4 characters will decode to only a single byte. For example, another way to interpret the padding character is to consider it as an instruction to discard 2 trailing bits from the bit string each time a equal is encountered. For example, when is decoded, we convert each character except the trailing occurrences of into their corresponding 6-bit representation, and then discard 2 trailing bits for the first equal and another 2 trailing bits for the other equal. In this instance, we would get 6 bits from the D and another 6 bits from the W for a bit string of length 12, but since we remove 2 bits for each equal for a total of 4 bits, the DWOR ends up producing 8 bits 1 byte when decoded. With the groundwork laid, let's now examine decoding base without padding and its connections to our previous discussions. Without padding, after normal decoding of 4 characters to 3 bytes over and over again, fewer than 4 encoded characters may remain. In this situation, only 2 or 3 characters can remain. A single remaining encoded character is not possible, because a single base character only contains 6 bits. and 8 bits are required to create a byte, so a minimum of 2 base characters are required. The first character contributes 6 bits, and the second character contributes its first 2 bits. For example, decoding without padding is not performed consistently among decoders. In addition, allowing padless decoding by definition allows multiple strings to decode into the same set of bytes, which can be a security risk. In this section, we'll be shedding light on variance summary table and its impact on our understanding of the subject. Implementations may have some constraint on the alphabet used for representing some bit patterns. This notably concerns the last 2 characters used in the alphabet at positions 62 and 63, and the character used for padding, which may be mandatory in some protocols or removed in others. The table below summarizes these known variants and provides links to the subsections below. In the following section, we'll be immersing ourselves in the captivating world of privacy-enhanced mail. The first known standardized use of the encoding, now called MIME Base, was in the Privacy-Enhanced Electronic Mail (PEM) protocol, proposed by in 1987. PEM defines a printable encoding scheme that uses base encoding to transform an arbitrary sequence of octets to a format that can be expressed in short lines of 6-bit characters, as required by transfer protocols such as SMTP. The current version of PEM specified in uses a 64-character alphabet consisting of upper and lowercase Roman letters OS, the numerals, and the plus and symbols. The equal symbol is also used as a padding suffix. The original specification additionally used the symbol to delimit encoded but unencrypted data within the output stream. To convert data to PEM printable encoding, the first byte is placed in the most significant 8 bits of a 24-bit buffer, the next in the middle 8, and the third in the least significant 8 bits. If there are fewer than 3 bytes left to encode, or in total, the remaining buffer bits will be 0. The buffer is then used, 6 bits at a time, most significant first, as indices into the string size, and the indicated character is output. The process is repeated on the remaining data until fewer than 4 octets remain. If 3 octets remain, they are processed normally. If fewer than 3 octets, 24 bits are remaining to encode, the input data is write-padded with 0 bits to form an integral multiple of 6 bits. After encoding the non-padded data, if 2 octets of the 24-bit buffer are padded zeros, 2 equal characters are appended to the output. If 1 octet of the 24-bit buffer is filled with padded zeros, 1 equal character is appended. This signals the decoder that the 0 bits added due to padding should be excluded from the reconstructed data. This also guarantees that the encoded output length is a multiple of 4 bytes. PEM requires that all encoded lines consist of exactly 64 printable characters, with the exception of the last line, which may contain fewer printable characters. Lines are delimited by whitespace characters according to local platform-specific conventions. In this section, we'll be deep diving into MIME, unraveling its complexities and uncovering valuable insights. The MIME Multipurpose Internet Mail Extensions specification lists Base as one of 2 binary-to-text encoding schemes, the other being quoted printable. MIME's Base encoding is based on that of the version of PEM. It uses the same 64-character alphabet and encoding mechanism as PEM and uses the equal symbol for output padding in the same way, as described at. MIME does not specify a fixed length for base encoded lines, but it does specify a maximum line length of 76 characters. Additionally, it specifies that any character outside the standard set of 64 encoding characters, for example CRLF sequences, must be ignored by a compliant decoder, although most implementations use a Krolf-Nullline pair to delimit encoded lines. Thus, the actual length of MIME-compliant base encoded binary data is usually about 137% of the original data length, though for very short messages the overhead can be much higher due to the overhead of the headers. Very roughly, the the final size of Base encoded binary data is equal to 1.37 times the original data size plus 814 bytes for headers. The size of the decoded data can be approximated with this formula. Bytes string length encoded string 814 1.37. Turning our focus to UTF-7, let's explore its key elements. UTF-7, described first in, which was later superseded by, introduced a system called modified Base. This data encoding scheme is used to encode UTF-16 as a SCII characters for use in 7-bit transports such as SMTP. It is a variant of the Base encoding used in MIME. The modified Base alphabet consists of the MIME Base alphabet, but does not use the padding character. UTF-7 is intended for use in mail headers defined in, and the character is reserved in that context as the escape character for quoted printable encoding. Modified Base simply omits the padding and ends immediately after the last base digit containing useful bits, leaving up to 3 unused bits in the last base digit. In this chapter, we'll be unraveling the enigma of OpenP and discovering its transformative power. OpenP, described in, specifies a SCII armor, which is identical to the Base encoding described by MIME, with the addition of an optional 24-bit CRC. The checksum is calculated on the input data before encoding. The checksum is then encoded with the same Base algorithm and prefixed by the symbol as the separator, appended to the encoded output data. Now, let's dig deeper into our FC3548 and unveil the hidden treasures it holds within. Entitled The Base, and Base Data Encodings, is an informational non-normative memo that attempts to unify the and specifications of Base encodings, alternative alphabet encodings, and the Base which is seldom used and Base encodings. Unless implementations are written to a specification that refers to and specifically requires otherwise, our FC3548 forbids implementations from generating messages containing characters outside the encoding alphabet or without padding, and it also declares that decoder implementations must reject data that contain characters outside the encoding alphabet. Let's now turn our attention to RFC 4648 and uncover the fascinating insights it brings to the table. Obsoletes and focuses on Base. This document describes the commonly used Base, and Base encoding schemes. It also discusses the use of line feeds in encoded data, the use of padding in encoded data, the use of non-alphabet characters in encoded data, use of different encoding alphabets, and canonical encodings. Now, let's delve into the intricacies of URL applications and explore its various aspects. Base encoding can be helpful when fairly lengthy identifying information is used in an HTTP environment. For example, a database persistence framework for Java objects might use Base encoding to encode a relatively large unique generally 128-bit UIDs into a string for use as an HTTP parameter in HTTP forms or HTTP GET URLs. Also, many applications need to encode binary data in a way that is convenient for inclusion in URLs, including in hidden web form fields, and Base is a convenient encoding to render them in a compact way. Using standard Base in URL requires encoding of and characters into special %encoded hexadecimal sequences becomes which makes the string unnecessarily longer. For this reason, modified Base for URL variants exist such as Basel in, where the and characters of standard Base are respectively replaced by and, so that using URL encoders is no longer necessary and has no effect on the length of the encoded value, leaving the same encoded form intact for use in relational databases, web forms, and object identifiers in general. A popular site to make use of such is YouTube. Some variants allow or require omitting the padding signs to avoid them being confused with field separators, or require that any such padding be % encoded. Some libraries will encode to potentially exposing applications to relative path attacks when a folder name is encoded from user data. Let's now zoom in on JavaScript DOM Web API and uncover the hidden gems that lie within. JavaScript DOM Web API. The ATOB and TOAD JavaScript methods, defined in the HTML draft specification, provide Base encoding and decoding functionality to web pages. The TOAD method outputs padding characters, but these are optional in the input of the ATOB method. Let's now shift our focus to other applications and explore the ways in which it shapes our perspective. Base can be used in a variety of contexts. A base can be used to transmit and store text that might otherwise cause delimiter collision. Base is used to encode character strings in LDAP data interchange format files. Base is often used to embed binary data in an XML file, using a syntax similar to data encoding. Base e.g. favicons in Firefox's exported bookmarks tool. Base is used to encode binary files such as images within scripts, to avoid depending on external files. Base can be used to embed PDF files in HTML pages. The data URI scheme can use Base to represent file contents. For instance, background images and fonts can be specified in a CSS stylesheet file as data arrows, instead of being supplied in separate files. Although not part of the official specification for the SVG format, some viewers can interpret Base when used for embedded elements, such as raster images inside SVG files. Base can be used to store or transmit relatively small amounts of binary data via a computer's text clipboard functionality, especially in cases where the information doesn't warrant being permanently saved or when information must be quickly sent between a wide variety of different, potentially incompatible programs. An example is the representation of the public keys of cryptocurrency recipients as Base encoded text strings, which can be easily copied and pasted into users' wallet software. Binary data that must be quickly verified by humans as a safety mechanism, such as file checksums or key fingerprints, is often represented in Base for easy checking, sometimes with additional formattings, such as separating each group of 4 characters in the representation of a PGP key fingerprint with a space. QR codes which contain binary data will sometimes store it encoded in Base rather than simply storing the raw binary data, as there is a stronger guarantee that all QR code readers will accurately decode text, as well as the fact that some devices will more readily save text from a QR code than potentially malicious binary data. As we enter this new phase, let's analyze applications not compatible with RFC 4648 Base from different angles and evaluate its significance. Some applications use a Base alphabet that is significantly different from the alphabets used in the most common Base variants. See variants summary table above. Encoding alphabet includes no lowercase characters, instead using ASCII codes 32 spaced through 95 consecutively. Encoding uses the alphabet updividual stock size. Avoiding all lowercase letters was helpful, because many older printers only printed uppercase. Using consecutive ASCII characters saved computing power because it was only necessary to add 32 without requiring a lookup table. Its use of most punctuation characters and the space character may limit its usefulness in some applications, such as those that use these characters as syntax. Inhex for HQX, which was used within the classic Mac OS, excludes some visually confusable characters like 7, O, G, and O. Its alphabet includes additional punctuation characters. It uses the alphabet updividual per stop size updividual. A UTF-8 environment can use non-synchronized continuation bytes as base, CUTF self-synchronization. Several other applications use alphabets similar to the common variations, but in a different order. Unix stores password hashes computed with crypt in the etsparse file using an encoding called crypt's alphabet puts the punctuation and before the alphanumeric characters. Crypt uses the alphabet updividual size without padding. An advantage over RFC 4648 is that sorting encoded ASCII data results in the same order as sorting the plain ASCII data. The GEDCOM 5.5 standard for genealogical data interchange encodes multimedia files in its text line hierarchical file format. GEDCOM uses the same alphabet as crypt, which is a digital size. Crypt hashes are designed to be used in the same way as traditional crypt hashes, but crypt's alphabet is in a different order than crypt's. Crypt uses the alphabet of digital size. Encoding uses a mostly alphanumeric character set similar to crypt, but using plus and rather than and. Encoding uses the alphabet of digital size. The pack, used with some terminal node controllers, uses an alphabet from X to XF. Bash supports numeric literals in Base. Bash uses the alphabet of digital size. Remember to follow me on social media for behind-the-scenes content and updates.